Lorentz Force equation. You may have noticed that the Maxwell equation doesn't have anything to do with the force. The force is such a fundamental law, but Maxwell handled only the field, magnetic field, electric field. Only force defined in the electromagnetic theory is so far Coulomb's force. And Coulomb's force is basically interaction between charge and the electrical field, and there's nothing to do with the force generated by magnetic field. Now, the magnetic field basically generate electric field, and the electric field act on the charge, and by the Coulomb's law, the force is generated. So there's no such a thing like magnetic fields directly generate a force. That's what we're going to show you here. Electromagnetic force on moving charge. So we have this equation. This is Maxwell-Ampere's equation, and we consider the time variant of D, means the boundary is changing around, okay? And time variant, we introduce the equation becomes like this. This is the boundary change, and this is the actually F variant by time, okay? And using a vector potential A, we modify equation. Vector potential is like a potential field. We have a vector potential we can use. We modify using that vector potential. Here's some mathematics to perform. So what's happened is if the surface is moving at the V, then curl E becomes time variant and moving effect. And if this is constant, then the force will be V times B. So that's the cause of the force. Basically, it's a electrical field. The Coulomb's force is acting on the charge. That's what the Lorentz force is about. So here, the force on the charge is generated by electrical field, which is generated by magnetic field. So there's no such a thing like electric charge directly interacting with magnetic field. So that's the important things. Now, if we add, we modify the equations. This is V, the current segment times B. The force is going to be on this segment. So when you have a current, not electric charge, and take this segment D and times B, the force is going to be generated D to B, this direction. So entire force is integration of this line, okay? So this is the famous Fleming's left-hand law. The force is I times B. Now, using that equation, we can calculate to see how much the horsepower we can get from the motor. The motor has a magnet and magnetic field crossing. And then when you apply the potential and the current go through, then you get force on n direction. So this is the force on n direction. From here, the spinning speed on the n direction is v. We can get the voltage required for this spinning, and that's the power consumption for the movement. Okay, you can look at the details in this video. I hope you enjoy listening. Please check out our videos. Thank you.